Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. Today we are going to continue and finish this part on index compression. But before we do, I have a question for you. And the question is this one. How many terms or types, or terms is the name of what you have on the left in the standard inverted index, the dictionary. How many terms can a 4,7 b plus tree of height 3 contain at least the minimum number of terms when you are at height 3? Remember that it grows, right? When you insert terms, it grows, and then you get more and more and more level. So what is the minimum number of terms for which you can actually reach height 3? The height means the number of edges between the roots and the leaves. Remember that in a B plus tree, all the leaves are exactly at the same level. So there's no maximum or minimum number of edges. It's always the same number of edges for every leaf. So height 3, 4, 7, B plus 3. Remember that the way we parameterized our B plus trees is that 4, 7 means between 4 and 7 children for every node, for every non-terminal node, right? So between 4 and 7 children. B plus 3 means that the leaves have the terms and the non-terminal nodes, so the non-leaves, they only have maybe terms, but for lookup only, right? So these are only virtual. So the terms are actually all on the leaves. So how many terms can you have on the leaves of that tree? 4, 7, B plus 3. (27, 48, 64, 96). These are numbers that look like there's been a lot of multiplications in there. So you can also maybe reverse engineer with trying to decompose them back into prime factors. But it's probably easier to really go the normal route of actually computing. So let's see what you have so far. 64. Okay. Are you sure? So this is amazing because I think that this is a case where the least of you got it correctly. But let's see why. Can you raise your hand, one of the two persons who said 96? Is there somebody in the lecture hall? Yes? Do you want to take the microphone and explain to us? Oh, you guessed, okay. On Zoom, maybe, if there's a student on Zoom? Otherwise, I will explain it. Nobody on Zoom either. So there's the mysterious second person who also said 96. Okay, so let's do the reasoning. So you basically, the values are on the leaves, right? And you basically have to do a multiplication, right? It's the number of children at every level times the number of children on the level below, times the number of children at the level below, and then times the number of terms that they are on every leaf, right? Who agrees with that? Right? So we just need to find the factors of that multiplication. So let's start at the root. What is the minimum number of children that the root can have? Who thinks it's 4? Who thinks it's 2? Do you remember the root is the only exception to the rule for the minimum of children. So it's 2 for the root because of that. So the root can have 2 children. So that's 2 times then how many? For the next level, what's the minimum number of children? Who thinks it's 4? Yes, it is 4 in that case, right? It's only the roots that can have less. So 2 times 4. So here we are already at 2 levels of edges, and then the third level, it's again 4, right? So 2 times 4 times 4. And now we are at the leaves. How many terms can there be at least on every leaf? Okay, let's do a poll. Possible answers, 1, 2, 3, or 4. Who thinks that there can be at least 1 term on every leaf? At least 2 terms? At least 3 terms? At least 4 terms? Okay, so here, remember that the number of values on every node is the number of children minus 1. You remember? If you can have 4 children, then it means you can have 3 values in between because the values are in between the children, right? So if you go left to right, you have the first child, a value, the second child, a second value, the third child, a third value, and the fourth child. So you can have 3 values, at least on every leaf. Between 4 and 7 children means between 3 and 6 values. That's the offset, right? It's the idea that if you have 10 trees, then you have 9 intervals between the trees. So this means that the number of terms at least is 3. It's between 3 and 6, so it's at least 3. So we have 2 times 4 times 4 times 3. 2 times 4 is 8, times 4 is 32, times 3 is 96. Right? So this is where the 96 comes from. Okay? As an exercise, you can try to compute the maximum number of terms, right? That could be in a 4-7 b plus 3. Who is now aligned with that result? Who understands how we come to 96? All right, very good. Okay, so now I'm getting back to my slides. So it means that it was a good idea to bring that back to your memory, right? As a good refresh of what we did back then. So again, if I summarize the main 2 things that you need to remember, the first one is that the root is an exception and can have less children than the minimum bounds, and the minimum bound for the root is always 2. The second thing to remember is that the number of terms per node is the number of children per node minus 1. So between 4 and 7 children means between 3 and 6 values. Okay, so let's then continue on index compression. So this is what we saw last time. There are 2 laws that are tongue twisters. It's Heap's law and Zipf's law, right? So remember that the first Heap's law tells us if we keep adding to the collection grows bigger and bigger and bigger and bigger. How does the number of terms, the number of unique terms, so that's basically the vocabulary, right? The vocabulary is the set of terms. The dictionary is the data structure that organizes that set of terms. So we basically look at the size of the vocabulary, the number of terms, how it varies if we increase the size of the collection, so the total number of tokens that there are in there, right? So we mean here the positional tokens, the actual ones you get right after you parse the documents. And so we saw that it's actually a square root function. That is very surprising. And the surprise is that at first you might have thought, and I thought that too, that the number of terms is capped, right? Because there are only so many words in a language, right? So I think that in the book, they say there are 600,000 words, maybe in English. It's actually one of the languages with the most words compared to French or German. That's because in English, there's many words that are doubles. Like, for example, you have to keep up, which is the Anglo-Saxon version, and to sustain, that is the Latin version. And you find a lot of pairs like that, so it basically increases the size of the vocabulary. But still, you would think it's capped, so it should stop at some point. So you might have expected to have some curve that eventually has some asymptote, and then it stops increasing. But no, it keeps increasing and increasing and increasing. And one of the reasons, the intuition behind that is that, especially if you go to the web, there are going to be names of people, there's going to be names of products, and so on and so on. And here it's basically unlimited, right? When you create company names, it doesn't have to be a word. You can just take whatever string you want as a company name. Okay, so that's Heap's law. And again, the surprising part here is that it keeps increasing and there is no actual limit to the number of terms. All right. The second law, Heap's law, is basically telling us if we look at the collection frequency, so the collection frequency is the number of occurrences of a term in the entire collection. So for example, words like the might appear a lot of time, then a also a lot of time, and then you rank them, right? So you basically sort the terms by decreasing frequency. Parenthesis, if you learn languages, that's exactly the way to go. Try to find the most frequent 1,000 words of a language and just learn them, and you already are 80% of the way. Anyway, parenthesis closed. Here, that's exactly what we do. We try to sort the words by decreasing frequency. And if we sort the words in that way, and then we plot that collection frequency, so the number of tokens that corresponds to each term, the number of times it appears in total in the entire collection, it turns out that we find an inverse function. It's basically 1 over the rec. So it's basically going to be k for the first one, then k over 2 for the second term, then k over 3 for the third one, k over 4 for the fourth one. And here also it's a surprise because the series doesn't converge, right? You know that if you sum the inverses of all integers, 1 plus 1/2 plus 1/3 plus 1/4 and so on, it doesn't actually converge. So this is yet another surprise here, that we basically have some curve here, the area of which is potentially infinite, right? If you go, it's also not capped. So you see there are a few surprises, but these are really empirical laws in the sense that we just looked at data, we just looked at the actual web pages and information we have, and this is what we basically find, right? And again, to find that, it's basically a linear regression on the log-log scale, because if you put on the log-log scale, these are actually straight lines. Okay, so that's Heap's law, and that's Heap's law. So now that we know that, that gives us a few hints about how we can now optimize the whole thing, because the goal of that lecture is to compress the size of the dictionary and to compress the size of the postings list. So knowing that is going to probably help us. Now, it turns out that we already did some compression. We just didn't call it that way, but in fact, we've already done some compression. Remember that we mentioned a few strategies when we post-process the documents, when we build the index. We can drop the numbers, we can drop the case, uppercase, lowercase. We can also remove stop words. So the stop words are those that appear very frequently. So there's a list of 30 commonly or 150 stop words. So we can drop them. We can also use stemming or lemmatization, you know, to group the words together that look alike. And in fact, all of those are actually compression techniques, right? All right. So if you look at how well they are doing, just going to be disturbed. No, I'm not going to be disturbed by this. Just going to. I'm not teaching cybersecurity. All right. So this is what we get when we actually decrease the percentages. So if we remove the number, we basically reduce the number of terms by 2%. If we case fold, then we reduce the number of terms by 17%. If we remove the stop words 0%, how can it be? Because we look at the number of terms. So if we have like hundreds of thousands of terms and we remove just 30, the impact is minimal. If we stem, then we are going to reduce the number of terms by 17%. Now, if you do it all together, you actually get minus 33%, right? This is, you cannot sum that, right? You know how it works with percentages. You need to multiply. So it would basically be 0.98 times 0.83 and so on and so on. And then you get minus 30%, assuming they are independent, right? So this is basically what we get, and that's actually already index compression. Then the number of non-positional postings, we remove the numbers, then that removes 8%. Again, I'm talking about the postings now, the non-positional postings. So no longer the terms, but the actual doc IDs that are in my index. So I remove 8% of the numbers with the numbers, then 3% of the postings go away if I do case folding. 30% of the posting go away if I remove stop words. So in that case, we remove 30 stop words. That's called the rule of 30, right? Removing 30 stop words typically removes 30% of the postings. And then stemming removes 4% of the postings, right? And here we basically gained 42%. It's not exactly the half of it, but basically almost half of it. Okay, then we have, so the impact on the number of tokens. So now this is the positional postings, right? So this is taking into account the number of occurrences. Now, if we remove the number, we get 9%. Case folding does nothing. The stop words now are very efficient, but this is precisely because the stop words are those that appear a lot of times, right? So half of the stop words, half of the tokens disappear, and stemming doesn't do much in that case. That's probably because stemming would primarily be efficient. I never know what way it goes, but basically it's more efficient for common words and less for the uncommon words that might be more invariable. So this is why it gives 0%, but overall, if you multiply all of that, we get 52%, minus 52% on the positional postings, right? So these are three perspectives. Again, either you look at the impact on the number of terms, so the height of your standard inverted index, or the number of the positional postings, so these are the doc IDs in your inverted index, or the tokens, which are the positional postings. So here that would be in a positional index, where you also have the positions of the terms. Okay, so basically we already did compression until now. We already know how to do a bit of compression, but can we do even more than that? And the answer is yes, absolutely. We can do more than that and go further. And we are going to start with the dictionary compression, right? You know that the standard inverted index is made of two parts, the dictionary on the left, which is the data structure, the B+3 that contains the term. So that's the dictionary. Then on the right, we have the posting list, but this we will do a bit later. We'll do them today, but a bit later. So let's start on the left. Let's try to compress the dictionary. Remember that dictionary is the data structure that allows us to look up the terms efficiently. So if we use a B+3, the complexity of the lookup is, everybody at the same time, you know that. The lookup here is logarithmic, exactly. So we have logarithmic lookup thanks to this. So this is called the dictionary, not to be confused with the vocabulary. The vocabulary would just be the set of the terms. The dictionary also has the structure. So basically, we have this structure, and we have the terms that are on the list, and these are the pointers to the posting list. By the way, since I have that slide, again, I remind you, 4 children, 3 values, right? 1 less than the number of children. And so another reminder, the root here has 2 children, it can have less. Okay. So when we have a structure like this, a B+3, the way it typically works is that if it's large, most of it will be on disk. All the leaves and so on will be on disk. And yes, there is a question on Zoom.
Is there not a point to be made that number removal and stop word compression effects can actually be added since the removed tokens are actually disjoint?
It was a very long sentence. Let me see if I can read it. Yes, absolutely. You could absolutely make that point. Generally, you have to multiply, but it is true that if you want to fine tune and be even more precise, then you can try to compute the total effect in a more fine-tuned way. It's an approximation, making the assumption that all the optimizations are independent, but of course, then you can fine-tune that approximation. That's a very good point, and that's very good critical thinking. Yeah, Thank you for this. Okay. So typically, the posting list will be on the disk. A lot of the levels of the B+3 will be on the disk. What you typically do is that the top of the tree you load in memory. So the beginning of the lookup, you have this all in memory. The rest you would load into memory as an as-needed basis, right? Whatever you need, depending on your lookup, you load into memory. You might even keep in the cache what you load very often, right? And the rest is on disk. It's important to have this in mind because it affects both the size that you have at your disposal on disk and in the memory, but it also affects the speed at which you actually access all of that data. But this is the idea. So I put a drive for the posting lists and a memory for the terms. Note that it depends on the size because you might have intermediate cases in which the postings lists are on the disk, but all the rest of the B+3 fits in memory, right? That can also happen. It's always important. This is actually a database thing. Whenever you store data on a server or in the cloud or in a cluster, you always have to ask yourself the question, does my data fit into memory? Then that's the best case because you don't even need to access the disk. Or maybe the data doesn't fit and you put it on disk, but maybe the index fits entirely in memory. And that is great when it happens. And then in the worst case, even the index doesn't fit in memory, and that will be slower. So this is also always something to have in mind. So let's look at a first inefficient, of course, approach to try to compute what we could do in terms of size. So imagine that all of my terms, I store them on 20 bytes. I'm going to assume, to simplify, that it's ASCII. Of course, you could also add more characters. Then you could, if you take 2 bytes for every character, of course, that changes it. But let's oversimplify. So 20 bytes, 20 characters for every word. 4 bytes, that means 32 bits for the document frequency. That's the purple case that goes along every term. And then we have 4 bytes if we are assuming that we only need 32 bits addresses for the pointers in memory, right? So that would be the older architecture. Now it's 64 bits, but you can still compress a little bit if you have less than 4 billion of them, right? So 4 bytes, and 20 bytes for each term. But now you see the problem is because, of course, if you want to store words like supercalifragilisticexpialidocious, that doesn't fit in there. So that's already a limitation of doing it this way. If you try to compress in this way, I think they have another example in the book that I think is hydrochlorofluorocarbons that also doesn't fit in there, but there are many, many others. So what can we do to improve? We have approach 2. Approach 2 doesn't constrain the size of a term. It doesn't say that you are limited to 20 bytes. Oh, by the way, I forgot to say, it's not only a problem that you have more, it's also a problem that you waste space because, for example, ETH uses 3 bytes and the 17 other bytes are just wasted, right? So this is another problem. Now, first improvement. We are going to put all the terms of the vocabulary as a single enormous string in memory, just concatenated after each other. And we are going to have pointers to the beginning of every one of the terms. So computer, CPU, data, ETH, information, retrieval, Zurich, maybe in alphabetical order. And if I have the pointer, then I can recover the words, right? I just need to take 2 pointers that are next to each other, and that gives me the beginning and the end of every word, right? Now, how much memory do I need? So still 4 bytes for the document frequency, still 4 bytes for the pointer. But now, since I also have a pointer, so the 4 bytes, that's the pointer to the posting list, right? But the 3 bytes here, this is the pointer to the term. So these are 2 different kinds of pointers. Why 3? Again, it's a matter of computing the size that you need, right? So 3 bytes would mean 24 bits. And that gives you 16 million, right? So you can cover, 2 to the power of 24, 16 million. So you can cover most use cases where, for example, we have 500,000 terms and so on. So 16 million, 3 bytes. And then you need to also take into account the size of the actual big string of terms. And here on average, you can run statistics in the English language. Typically, you would need 8 bytes in average for every word in there. But you see that now we are more efficient because we replaced the 20 bytes of before with 3 plus 8, 11. So we are down from 20 to 11. Who sees that this is more efficient? Okay, that's great. So you see it's simplified, of course, but here we can see that doing it that way is an improvement over the first version. Plus, we are no longer constrained by the 20 bytes maximum size of every term. So now we can store supercalifragilisticexpialidocious without any problem. Here's yet another improvement. Can we do even better? Yes, we can do even better. And in order to do even better, we are not going to put a pointer for every single term, but we are going to do it every k terms, right? So maybe every 10, every 20, every 5. That's a parameter you can adjust, but we do it every k terms. But we still need to be able to decipher the list stack, right? So it means that we need to add stuff to the list so that we know when the words end, right? Because now between these 2 pointers, I have k terms in there. How do I know where they stop? I have to add a bit of information. What I can add, for example, is the number of bytes of every term, 8 for computer, 3 for CPU, 4 for data. Again, that's assuming ASCII in the simple use case. So now you know where this ends because you just look at the bits that give you the size. So this is always a fixed size. So you can, how many bytes do you think we can take here? We can take just 1, right? 1 byte is enough because 1 byte to encode the size goes all the way to 256. I don't think that there is any word in English that has more than 256 letters, right? So here we can just take 1 byte, 1 additional byte every time, and that's it. So now we went up from 8 to 9 bytes in average because we added this little one here. But the number of the size of the pointers is reduced because we had 3, but now it's 3 divided by k because we have k times less pointers in there. So now the total sum is 4 plus 4 plus 3 over k plus 9 on average for every term. So you see that we went from 20 to 11 to now 3 over k plus 9. And if you increase the value of k, that becomes closer and closer and closer to 9, right? So the difference is no longer so dramatic, right, as between 20 and 11, because here you when you increase k, you will bump against the 9, right? So, but still you can get a bit closer and grab a few more bytes that you can save. For whom does that make sense? This is called blocked storage. This is called a full string. This is called blocked storage. And you can analyze a little bit. So just to give you an idea of how this is analyzed here, without blocking, you can basically emulate the lookup time with a binary tree like that. If you block, so you can compute the number of memory seeks that you need like this. Why is it like this? Because technically, it's a binary search. If I go back here, you can do a binary search, and that's the number of lookups that you have in here. If you have a block, then it means that you have these groups of terms that go together, and then you do a binary search based on the pointer, but there's only a pointer every k terms. And then the k terms, you have to access them linearly, right? When you look up a term, once you know in which block you are, that's a linear search. So it means that you're paying a price, right? We gain in size because we save on space with these blocks, but we lose a little bit on performance because that's going to be a tad bit slower to access them, as you can see in here, right? So you can even compute the average, but on average, it's a bit slower. So if I come back here, again, if I summarize, here I have 8 bytes on average in addition to 4 plus 4 for each term. And I have kind of the optimal binary search case. And here I gain a bit of space by having a pointer every k terms, but I lose a bit in performance because my binary search will kind of not be perfect because I have to end with a linear complexity here for the k terms within the same block. For whom does that make sense? Very good. So you see that it's always a compromise, right? You have a compromise to make between the size that it takes on disk or in memory versus the time that it takes first to build the index, but also to look up at runtime with the queries. So there is no free lunch, but as computer scientists, that's not the first time that you hear this, right? You have to make a compromise between the space and the time, the algorithmic complexity. Okay, so it's a compromise that I already showed you. Okay, that's only a visual of what I mean with that. The fact that it's the complexity is less good because now you have this kind of structure in the search. These trees do not actually exist. This is only a representation. Okay. What do I have here? Yes, it's yet another optimization. So in my previous example, I just put random words in there. But in real life, it's going to be looking more like this, like automata, automate, automatic, automation. I mean, it feels more like when you look in a dictionary, what it looks like. But do you see that this can be a bit optimized here? Because there's a lot of repetition. Automata, automate, automatic, automation, and so on. So can we compress even more? Maybe, right? We could take the prefix. Every time it's automate something. So we can just put automate just once, then a little symbol like a star or whatever, and then we only put the suffix after that. So this is just a compressed version of that. This takes less space. We just factor out the prefix that is in common for the entire list. And since these are adjacent terms in the dictionary, in every one of these groups of K terms, you're probably going to be able to save further doing that. Whom does that make sense? Okay, so that's great. So what do we gain here with this approach? With the fixed width, we would be at 11.2 megabytes. That's an example on a specific collection of 960 megabytes, but it's just to give an impression. So we had 11.2 megabytes. If we use these unique strings and pointers, this huge string with the pointers to the beginning and end of the terms, we are down to 7.6. That's when we went from 20 to 11, remember? Then the blocking from 7.6 to 7.1. Again, it's not a surprise because I told you there's this 11 and the best we can get is 9. If we take a huge value of K, we still bump against the 9, right? So here it's not surprising that the blocking is not going to be huge, some effect, but not huge. The blocking and front coding, however, have a more noticeable effect. But again, this is what you saw here, right? You do see the effect in here. So here we are down to 5.9. Compared to 11.2, we kind of gained half of it, right? So this is quite good, right? So that means we can squeeze twice as many terms in the same amount of disk and memory, right? So this is good. We've done well with the dictionary compression. So now we can move over to the postings list compression. There is a question.
Yes, there is a question, but again, it's a longer one. So for the front encoding, how do you decide where to do a break? In an extreme case, one could use all the words which start with an A and take A as the prefix and the rest of the words as a suffix, or more sensible like automat. So like, how is this decision made?
So the way that I think about it, if you look at here, when do you do that? You do that within a group of K terms, right? It's not the whole dictionary, it's just a group of K terms. So if you have a reasonable value of K, then that kind of gives you basically in that group of K, you take the common prefix, right? It might not work, of course, if you have an abrupt change, like for example, you're at the end of one letter and begin with another one, then you can just cut it in two, right? But basically, the group of K terms gives you the constraint on the way you do it. Does that make sense?
Yes.
Yep. Awesome. So what I give is the idea, right? When you implement the idea, it might be a bit more complex, right? But this is the general idea is like this. Okay. So this is the dictionary compression. That's the first half of what we are doing. That's what we've been doing. And now let's proceed to compress the posting list. What is the posting list? What is a posting? You might remember that a posting is a pair. It's a pair that contains a term and a document. We even compress them while building the index to term ID and document ID, but technically it's a pair, term documents. However, in the standard inverted index, you notice that all the postings on the same row, they have the same term. So we are not going to store the term in every one of these postings. We just put it on the left once and for all. So it means that the actual posting list, when they are stored, it's just document IDs, right? What is a document ID? It's an integer. It means that a posting list is a list of integer. Now it feels more mathematical suddenly, right? We are basically back to how do we encode a list of integers efficiently? How do we compress a list of integers? Okay. So it's one of these lectures where we can suddenly enjoy some mathematics. Now, if you don't optimize anything, you might think, okay, let's take 4 bytes. Again, 4 bytes, is it reasonable or not? 4 bytes is 32 bits. So it means you could basically store 4 billion documents. If you are managing a library, that makes sense. If you're trying to index the web, maybe not. Maybe 4 bytes then wouldn't be enough. But it's just an example like in which we would have 4 bytes, meaning at most 4 billion documents, right? 2 to the power of 32. Yeah, I even did the math right there with the exact value. Can we encode with less space? Obviously, yes. Otherwise, I wouldn't be doing this lecture in front of you, right? So yes, we can absolutely encode this with less space. And here is the first idea. These posting lists that I told you about, they are not just lists of integers. They are sorted lists of integers. Right? It's a sorted list. It's an increasing list of integers. So, for example, let's take a very frequent term, right? So that might almost be a stop word. We have all of these integers. It increases. Imagine that we store every one of these as 4 bytes, right? I didn't put 4 bytes, of course, here for the slides, but that's the idea. Do you see how we can improve here in terms of storage without losing any information? Can I improve on that by storing in less space? Any idea? Anybody? Yes, go ahead. Maybe the microphone. And oh, yes, wait. Because I'm protecting your ears because otherwise it's basically having this noise all the time. Go ahead.
I'd assume in this case, it would start really low as well. So we could just store the difference in between 2 words and then do it fixed like that. If it starts with a high number, yes, we could start with a prefix, but that's also just the difference between 0 and this number. So I guess just the difference in between terms.
Yeah, absolutely. This is correct. These are small gaps, so we can just encode the gaps like this. So this is exactly what you described, right? Yeah, we get back to you.
Someone in the Zoom chat also had the idea of using prefixes again.
Oh, prefixes again. Yes, this is true. You could also imagine doing it with prefixes that would reuse the same idea. The gaps, I think, since these are integers, might even be more efficient, but the prefixes would have worked too. Then you would basically have considered the integers as written in base 10 and then took it from there, right? I think that technically doing it with prefixes or with gaps is almost isomorphic. It's always an idea of decomposing into 2 parts, one that is common for all and then a difference, right? Okay. Oh, there is a difference with the prefixes because the prefixes would all be with respect to the first one. So it means we would encode the difference with 1056 with the prefixes, but the gaps here are not all with respect to the first one. It's always with respect to the previous one, right? So there is a tiny difference between the two. Yeah, but both ideas are very good. And the one that you mentioned with the back gap encoding is exactly the way to go. In fact, it's such a great idea that we're always doing it, right? It's an increasing list of integer. We are anyway going to encode the gaps, and that's even often implicit every time that we encode the gaps. Okay? But this is only going to be efficient for frequent terms, right? Because if you want to encode a posting list for a term that is rare, then the gap, that will not help that much, right? So the most effect that it will have are for the terms that are rather frequent and for which the gaps are going to be small. And in fact, it means that the distribution of the gaps varies from term to term, right? So if you want to do it uniformly, that might not be very efficient, right? So in that case, it's a fixed encoding, right? Every gap is encoded with 4 bits, right? If it's a fixed size, you need to ask yourself, what is the maximum size of a gap, right? But if you think of it, what's the maximum size of a gap? The worst case is that you have a very rare term, and then the size of a gap can be at most, again, 4 billion. But then you're back to square one, because you're, again, storing 4 bytes every time. So it means that we need to be smarter than that. We cannot just have a fixed number of bytes for every gap. We need to vary it. So we need to look at variable byte encodings. It means that we need to vary the number of bytes to be more efficient. But there is something we need to consider, is that when you have a fixed number of bytes, it's easy because you know where they start and you know where they stop, right? So you know that in that case, if you have, in the end, it starts as a sequence of zeros and ones in memory. So if you have 32 bits, you know that it's always that. You always know when they start and you always know when they stop. So that is very, very easy to actually retrieve them. But now, if we have a variable length encoding and the number of bytes that we use for every gap can change, it can be just 1 byte if it's a tiny gap. It can be 4 bytes if it's a very large gap. We have the problem that we don't know anymore where the boundaries are. And since I put everything as a sequence of zeros and ones, then go figure where they start and where they store, when they stop. So we need to solve that problem, right? And the way that this is typically solved, it's called a prefix code. We need to have a way that if we read that from the left to the right, we have enough information in the bits that we read to know when to stop. If we have that, this is called a prefix code. There is an example of prefix code that you might all know, which are the phone numbers, right? Because when you dial on a landline, at some point it will stop because it knows that the phone number is done. And it means that the phone number system is a prefix code. So if I gave you hypothetically a list of phone numbers, but I don't tell you where they begin and when they end, then you will be able to figure out when they start and stop. Who would be able to do that? Right? You know, for example, you see 00, so you know that's an international number. 1, that's the US, 650 area code, probably somewhere in the Silicon Valley, then 7232300, and then you're done, right? So you know it stops here. 117, you know it's an emergency number, only 3 to read. Then 044, that's a number in Zurich, 630, that's ETH, 1111, and then it stops. So you see that I wouldn't need to tell you where it starts and when it stops, because if you read it from left to right, because of the way that phone numbers work, you know exactly when they stop. That's just an example, but basically we want to simulate the same thing, right? With prefix codes. It turns out that there is a very good example that actually works, that's UTF-8. UTF-8 is an encoding for Unicode characters, and that is variable. For example, if you try to encode a character that has at most 7 bits, then you can encode it in just 8 bits. You put a 0, right? And then the 7 bits of the character. So you see that if it is an ASCII character, then that's 8 bits, that's 1 byte, 1 packet. Pi needs less, at most 11 bits, right? So this is a more complex character. What you do in that case is that you encode it in 2 bytes. And the way it works is that you have the ones that are marked as red and not bold. 110 tells you this is the first of 2 packets, 110, and these are the actual bits that come from here. And then the 10 tells you this is a continuation packet, right? So 10 and then 000, right? So then you can get back this number. If it's even more, so the euro symbol is even more recent, so this is at most 16 bits, then you need 3 packets. Then you have 1110 that tells you this is the first of 3 packets, then 1010 that basically encodes the continuation. So this is an example. called UTF-8. And by the way, if you need to implement a new system with strings, always speak Unicode, and UTF-8 is probably your best choice by default to be internationalization ready. Okay. Now, this is a bit complex, UTF-8, but this is because it has other properties than just these. It also is auto-synchronizing, right? You can technically, if you're right in the middle, completely lost in the middle of a text encoding as UTF-8, you can figure out where the next character is, right? But we don't need that in our case. So we can do simpler than that. And the way we can do variable byte encoding is just with a single bit at first that tells us this is the start or this is the continuation. Sorry, this is the end. So an example would be, for example, 4, which is 110 in base 2. You just encode it as a single sequence of bits, and you put in front a 1. The 1 tells you it ends here. This is the last one, right? So this is how you encode if there are at most 7 bits. I should have put at most rather than less than. Then if it's between 8 and 14, you just cut it into twice 7 bits, and then you add back a 0 on the first packet because that doesn't end here, and then a 1 to say it ends here, right? So in the general case, you're going to have a lot of bytes starting with a 0, and then at the end, a byte starting with a 1 that tells you this is the last byte. Okay, for whom is that clear? Right? This is called variable byte encoding, right? I only use 7 bits of every byte. The first bit is reserved for telling is it the last one or not the last one, and the other 7 bits are used for the actual encoding. So you take the number, put it in base 2, pad it with zeros so that it's a multiple of 7, the number of bits, and then you insert a 0 on every packet of 7 bits, except for the last one where you put a 1. For whom is that clear? And I have more hands. So you deserve the break. Let's take 15 minutes. I'll see you at 11:15, and then we'll continue to encode and compress and compress and compress even more. Thank you very much.